All right, so welcome back to the next installment of our Fields Academy course on optimal transport. I got by midnight last night, I'd received 12 assignments, so that's I don't know if I should expect any more or not, but at least 12 came in. I know there's one person that was sick, and so he'll get his in much later. But and it was sort of interesting to me that I think 8 of the 12 were maybe from U of T graduate students, but then one from McGill, one from Western, one from McMaster, and one from University of Texas at Austin. So. I'm going to share my screen on my tablet. And put OneNote up. There we go. Lucy, are there any questions, problems, difficulties? So, so I found myself a little bit pinched for time at the end of last lecture, and I realized that I mean, things would have been much simpler. So I wanted actually to state and prove a lemma, and that would have made things much simpler in the proof of the final theorem. But it's a useful lemma for other purposes as well. So here's the lemma. So try that. So let me see. As usual, m plus and minus are Polish. And mu plus is a probability measure on m plus, and gamma is a joint measure. So gamma, I guess, will be it's a joint measure on the product space. I don't really care what the target is, but the target is some Borel probability measure on the target space. And so if I have a map on a subset of m plus that's hopefully defined mu plus almost everywhere. So if G takes, maybe it doesn't have to be defined absolutely everywhere. So I'll call the set of points where it's defined the domain of G. And gamma of graph G has full mass where the graph of G is exactly what you expect it to be. It's the set of points x G of x, such that x is in domain of G. Then, so there are two parts of the lemma. Then G is mu plus measurable. And gamma is the push forward of mu plus through the identity cross G. So what I like about this lemma is that the measurability kind of comes for free. So I don't need to assume measurability of G as a consequence. And actually, I guess that this is slightly more general. So I guess that let me make a few changes. I guess that it would be enough that mu plus and minus are non-negative measures and sigma finite. And then I would have to replace this condition by I would have to ask that gamma of the complement of the graph be 0. And so I should say maybe maybe a word about mu measurability. So probably you're familiar with the fact that the Lebesgue sets are bigger than the Borel sets. There are more Lebesgue sets than Borel sets because the difference between the Lebesgue sets and the Borel sets is that in not every subset of Rn that has Lebesgue measure 0 is a Borel set. Nevertheless, whenever you have a measure, you can complete the sigma algebra on which it's defined by including all the sets of measure 0 in that sigma algebra. So, i.e., with respect to the completion of Borel sigma algebra by sets of mu measure 0, mu plus measure 0. So this, in other words, this construction by which you get the Lebesgue sets by the Borel sets is a general construction that you can do for any measure. Right, and then it says if basically what this lemma says is that if gamma lives on the graph of a map, then gamma is given as the image of its left marginal under the identity map cross the map whose graph it lives on. And this is what's cute about this lemma is that this is the place where you see where Polish comes into things. So let's see. Let me make some remarks. So one of the nice things about finite measures as opposed to infinite measures is that they are their inner and outer finite non-negative measures. They're on appropriate spaces is that they're inner and outer regular. And what that means is that mu plus of any, I guess, Borel set is given as the inf over open, be contained in U open, U plus of U. So that's what it means to be outer regular. And what it means to be inner regular is it's the sup of mu plus K over sorry, B should have been just B, not B plus. Come back. B containing K closed. And M plus Polish means that actually you can get away with just taking compact sets here. So in other words, the measure of any set can be approximated from the inside by compact sets. And I guess that this would be true. I don't even really need if I'm willing to let this be the outer measure, then I don't even need B to be Borel. And if B is Borel, then it's the measure. And okay, so that's this kind of this observation that you can, and so sometimes this is called the Radon property. That you can do inner approximation by compact sets up to sets of arbitrarily small measure. Okay, so this is so now I'm going to prove the lemma. And somehow these observations about Polish spaces and approximation from inside by compact are crucial to this business of getting the mu measurability for free. And so how does this go? This goes that So if the graph G, the complement of graph G is gamma measures 0, then it must be gamma measurable in the sense of this completion. And so that means graph G is gamma measurable. And so that means that I can approximate it from inside by compact sets. Right, if I was not dealing with probability measures, I have to write the limit of the complement of gamma measure of complement of Kn goes to 0. And so if I take the union of these guys, right, I could even take these compact sets, since the union of two compact sets is again compact. I could take these guys to be nested. And so if I take the union of these nested compact sets, I get a set which is sigma compact and has gamma full measure. And my claim is that so let me let xn be the projection of Kn onto the first coordinate. And although it's, so this is sort of a subtle point in set theory. If you take a Borel set and you project it onto the first coordinate, it might not be Borel anymore. But if you take a sigma compact set and you project it onto the first coordinate, since projection is continuous, it's sigma compact again, because the projection of a compact set, the continuous image of a compact set is compact again. Sorry, I guess it's compact. Sorry, the Kn is compact, and if I let x infinity be the projection onto the first coordinate of K infinity, that's sigma compact. And so I claim that the graph, the G, is continuous when restricted to the projection onto one of these finite things, and that this continuity follows from compactness of Kn. So let's see, how does the proof of this claim go? So I don't know what I should say. Claim 1, proof 1. Suppose if I had a sequence of points xk in xn with x infinity equals limit k goes to infinity of xn, xk rather. What does it mean to be an xn? It means that there exists yk such that xk yk is in Kn, which is contained in graph G. So in particular, yk is G of xk. And but I guess by the compactness, since the projection of a compact set is compact, I know that X is in, sorry, XK again. And so, great. So this limiting point is in XK. And what am I trying to do? So by the compactness of Kn, every subsequence of Yk admits a convergent subsequence Ykji going to a limit y infinity, and we'll show y infinity is g of x infinity. And so if I can do this, then I claim I'm done, because if I had two different subsequences that converged to two different limits, but both limits agreed with this thing, then the union of the two subsequences would be converging to that limit, and that means that the whole sequence is converging to that limit. Okay, great. So in fact we're done, because, but of course the compactness of Kn also implies that x infinity, y infinity is in Kn, and that implies that y infinity, because Kn is contained in the graph of G, that implies y infinity equals at G of x infinity. Right, so that's the end of the claim. So we just checked that G was continuous, at least on this projection of these things. And so basically, when I have this increasing sequence of sets, since the Kns are nested, that implies that the xn minus 1 is contained in xn, and eventually it's contained in x infinity. Since I have this increasing sequence of nested sets, and I have the restriction of G is continuous on every one of the sequences, at least the limit, the G on x infinity is at least Borel, because it's a limit of continuous maps and up to sets of measure 0. Basically the, okay, so what did we say? We said that gamma of k infinity was 1, and because gamma has left marginal mu plus, that implies that mu plus of x infinity is 1. And the xn's, gamma kn being close to 1 tells you that mu plus of xn is close to 1. And so since mu plus of xn goes to 1 equals mu plus of x infinity, G taking x infinity into m minus agrees is a limit of continuous maps up to a set of measure 0. And so now we've kind of gotten measurability of G outside of a set of measure 0. So we've got mu plus, i.e. G is mu measurable, mu plus measurable. And you can see, so somehow, let's see. So I wrote this argument down with Ahmad and Kim and myself about 10 years ago, but you can also see a very similar argument in Ambrosio's book. Ambrosio Bruet's similar book. And again, they do something slightly differently, but it has a similar flavor. They take advantage of the inner regularity and compactness and so on. This is I can't even remember the journal. Actually, it's like mathematical bulletin something. It was a new journal. This appeared in the first issue of the journal at the time. Okay, so now so somehow we've showed the measurability, mu plus measurability, and then we want to show this fact also, that gamma is given as the push forward of mu plus under this map, which maybe is not too surprising at this point. And this is what I was kind of doing last class, stumbling through. So now if I have a Borel product, and what do I want to say? I want to say if I intersect that Borel product with, oh, maybe K infinity should work. Or maybe graph G. What would I expect? I would expect that for a point to be in here, it has to lie on the graph of G. So the first coordinate has to be in U, and the preimage of the second coordinate the first coordinate also has to be in the preimage of the second coordinate. So this is since K infinity lies in graph of G. Right. So you can check any point over here lies in here, and any point over here lies in here. And then you hit this thing with gamma. Oh, maybe wait a second. Maybe I also want to intersect with something like U cross U minus. That doesn't cost anything, because this is right. Yeah, that doesn't cost anything because these points are already in U. And I don't know why that was. Maybe that wasn't a useful thing to do. Oh yes, sorry. I got this wrong. It should be cross mu minus here, because K infinity is a subset of the product space, and this is a subset of the first space. And so the second coordinate can be anything, provided that the first coordinate lies in the preimage of V. So you show that these two things are equal as sets, and then you apply gamma to both of them. And since K infinity is full measure, whether you intersect it with and gamma measurable, whether you intersect it with K infinity or not is kind of irrelevant. And then because the left marginal of gamma is mu plus, and I'm producting with the whole space here, this is mu plus of U intersect G inverse V, and that defines, that's exactly what it means to be gamma cross G push forward of mu plus evaluated on U cross V. And so we've showed that gamma is identity cross G push forward mu plus as advertised. Are there questions? And so this lemma, which says that as soon as you can show that you're, that if you're supported on a graph, or at least concentrated on a graph, so in other words, that the complement of the graph has zero outer measure for gamma, then you're done because the function is u plus measurable and gamma is given in this way by the function. And so I had this theorem last class. I don't know, maybe it's worth to repeat or to restate it. So the theorem was that if M plus was a manifold and mu plus was absolutely continuous with respect to Lebesgue coordinates on that manifold, and C was a continuous cost function twisted, and whatever locally Lipschitz in X and X uniformly in Y, then I had these three consequences. Then mu plus and minus were probability measures. Then the claim was there exists a u, which is its own second conjugate, such that G defined as, I think I called it capital Y, but it's also sometimes called the B exponential of gradient U, has G pushing forward u plus to mu minus. And G, only one such map arises in this way. And gamma's identity cross G push forward mu plus uniquely solves Counterexamples. So in other words, the Counterexamples problem has only one solution, and it's supported on the graph of the map, and the map is the map from part one. And that's a little bit, this idea of being supported on a graph of a map. So you guys, those of you that did the homework, there was this, the third problem was to show that if you look at the matrices whose columns and rows all sum to 1, or maybe sum to 1 over the dimension of the matrix, then let's say all sum to 1. Square matrices, n by n matrices whose columns and rows all sum to 1, that forms a convex polytope, and the polytope has exactly n factorial vertices, and the vertices correspond to permutation of the rows against the columns. So you can think of this as being some kind of analog of that, where, so in other words, each row corresponds to a single column and vice versa. And so here, living on the graph of a map says that each y corresponds to gamma, or almost every y corresponds to it, sorry. Almost every x under gamma gets mapped to a single y. And so indeed, the lemma makes the heart of this theorem to show that, just somehow that there is a gamma supported on the graph of a map that optimizes, and then you get conclusion 3 out of that. So maybe let me make the remarks about the proof once more. Since I tried to cram it into 5 minutes yesterday and it was not all that, I'm not convinced it was all that successful. So the proof is we take, so there exists gamma and UV equals V conjugate U conjugate such that support gamma is contained in the B subdifferential of U. So that came out of, for example, by choosing gamma maximal and the Rockefeller-Roche theorem. And then if we can show that gamma is supported on the graph of a map, then we'll have 0.3 if the map is of the form 1. And basically we get that because recall, since U is a transform of something or its own second transform, it inherits Lipschitz continuity locally. Local Lipschitz continuity from B I know that it's going to be differentiable mu plus almost everywhere by Rademacher's theorem. Well, it would be differentiable Lebesgue almost everywhere in coordinates, and we've assumed that any Lebesgue set of measure zero is also a set of measure zero for mu plus. And so that tells me that now if xy is in the subdifferential of B intersect this set of full measure domain U cross M minus, what it means to be in the subdifferential of B is, let's call this x naught, y naught. U of x plus Vy minus By is non-negative, and equality at x naught, y naught. And of course, it's important that we're talking about a manifold like the interior of a manifold and not a manifold with boundary, because I want to be able to differentiate at x naught and claim that if the function is minimized at x naught, then its derivative is zero. And I couldn't do that if I was on the boundary of the manifold. Got to be in the interior. So since I'm in this point set of differentiability, I can differentiate this thing at x naught, and I get du of x naught equals dxb of x naught, y naught, and that says that y is equal to y naught is equal to the what we call the b exponential, which we assumed existed. We assumed that was invertible. That was the twist hypothesis. B exponential of x naught grad u. And so let's define this to be G. And since this is a set of full gamma measure, it's G is basically defined on the projection of the subdifferential into the first coordinate. And since the support of gamma is contained in that subdifferential, G is defined mu plus almost everywhere. And so we just showed that up to this set of measure zero, this is contained in the graph of G. And so now from gamma vanishing outside the subdifferential, we see that up to a set of gamma measure zero, gamma vanishes outside graph G. And the lemma implies the conclusion. Great. So, well, okay. So we started. So, for example, we started by choosing gamma maximal and knowing it had B cyclically monotone support, and therefore the Rockefeller-Roche theorem applied. So basically, we just showed that any gamma maximal will be equal to this guy for this G, which was defined in terms of U, and a priori it didn't necessarily depend on gamma. And so we've just shown that we have a unique maximizer for the Kantorovich problem. And again, because, well, if you project this relationship, So 3 is proved. And if you project this, if you compose this relationship with projection onto the second coordinate, you get that mu minus equals g push forward mu plus, basically because whenever if you have a map from one space to another and a map from the second space to the third space, and you have a measure over here, then here you get f push forward mu plus, and here you would get g push forward f push forward mu plus, but that's also g composed with f push forward mu plus. So somehow applying this kind of functorial reason to this, composing with the map projection on the second coordinate, we get this thing here. And so that verifies 1. And finally, to verify 2, is slightly, one has to do something slightly roundabout to verify 2 using this. So let's see if I can say it. So for 2, if u hat equals, if I had some other u, which was its own second transform, and such that g hat given by d exponential du hat also pushes forward, has g push forward mu plus equals mu minus. So I can't conclude quite yet. I need to do a bit more arguing. Then I would need to argue that I need to argue by duality. I need to argue that u hat and its transform also minimizes the Kenner-Roach dual problem. So gamma, which would be the image, would be a B maximizer. And so it would equal, so let's say call this gamma hat. So it would equal. And now I'm helped, although g hat pushing forward mu plus is not enough to conclude that. So you can have this relationship. So, and g hat and g can be very different. So for example, imagine a Gaussian measure and the identity map and a rotation of that Gaussian measure, the standard normal distribution, a rotation of the standard normal distribution around its center. The rotation is not equal to the identity map, but they both take the standard normal distribution to the standard normal distribution. So this does not imply that g hat equals g almost everywhere. But this does imply, this implies that g hat equals g mu plus almost everywhere. And I can try to say what the picture behind that is. So and so that's the uniqueness, that the map, there's only one map that arises as the exponential of the derivative of a B convex function. So the picture for this is that if you didn't, by contradiction, if g hat is not equal to g mu plus almost everywhere, you could find a set of positive measures. This is m plus and this is m minus. There exists a u of mu plus positive measure where they're very different. Let's say like this. So like g hat and g. Let's say the distance in mu minus between g hat of x and g of x is bigger than some epsilon bigger than 0 for every x in u. And then you also you would also use that somehow these Borel maps, just like so what's one of Hardy's principles? Hardy's principles are that measurable functions are almost continuous, right? So somehow when you throw away a set of very small of a small measure, then you can make a measurable function continuous. So apart from the set of small measure G and G hat are continuous functions. They're approximately continuous. And so you sort of choose a point of continuity for both of them. And that's some of the picture that I tried to draw here. So G is almost continuous to X naught, G hat is almost continuous to X naught. And the measures identity cross G, but they take very different values like Y naught and Y1, which are quite a distance apart. They're distance at least epsilon apart. So identity cross G push forward mu plus on something like a small enough ball around X naught cross a small enough ball around Y naught is going to be positive, but identity cross G hat push forward mu plus at the same, what should I call this, Z is going to be 0. And that would, so that in that way we get a contradiction. And so because we're looking in the product space at identity cross, and because these two things are equal, that tells us that they're equal mu plus almost everywhere. Other questions? All right. Great. And so now if we think back to Brenier's theorem.
Well, Robert, yep. I have a question. So if we weaken the hypothesis of mu plus being absolutely continuous, yes, we can still define the G as the exponential of the differential of the counterexamples potential. Yes. So would that still give me like some information, or would it be? Sorry, I don't know if you can.
How much do you want to weaken the hypotheses?
I'm not sure. Like I don't know if there's like a weaker version, like other sure, than giving 0 to small sets, right?
Oh yeah, there is a weaker version, and so in some sense, the weaker version goes back to my Duke paper from 1995, and then it got and also myself, and then it got sharpened a bit by Gangbo and myself in 96, and then somehow the ultimate version of this was by Nicolas Gilly in maybe 2011 or so. It can be sharpened if you're willing to assume a bit more smoothness from the cost or the benefit function. So somehow we basically assume the benefit function was Lipschitz in X. And that told us once differentiable. If we're willing to assume the benefit function is something like C2 in X, or uniformly C2 locally in X, uniformly in Y, or at least C11, so in other words, has Lipschitz derivatives, then that would tell us that, so if B Y is, say, C11, locally in X, uniformly in Y, that would imply that U is semi-convex. So the second derivative of U is a measure, and the measure can have singularities that go to infinity in the positive direction, but they can't go to infinity in the, i.e., second derivative of U of X is bounded below by some constant times the identity matrix. And here I mean the weak, whatever, distributional derivative in case. So I allow singularities, but they have to be, you can't go to minus infinity in the negative direction, only in the positive direction. And so then there's another nice theorem. So in one dimension, a convex function has a non-decreasing derivative, and in fact, non-decreasing functions are defined, they're continuous except at countably many points. They can only have countably many jump discontinuities. And there's a natural generalization of that to higher dimensions, which says that U on Rn convex implies that du exists except on, there are different ways to say it, except on a set of dimension, of Hausdorff dimension n-1, which would be except at countably many points in the one-dimensional case. So in fact, I'm going to say something technical for those of you who have seen some geometric measure theory, which is probably not many of you. So let's see a show of hands. How many people know what Hausdorff, have an idea what Hausdorff measure is? And how many people, so now I'm what do you call it? I'm hamstrung by the fact that I can't see all of you at once. And I'm wondering if there's a way that I can figure out how many people, so how about showing, now everyone put their hands down. How many people do not know what Hausdorff measure is? Anyone not know what Hausdorff measure is? There's one person. Okay, great. One person doesn't know what Hausdorff measure is. What's a good reference for Hausdorff measure? I recommend, there's a couple of you. Okay, so let me say a few words about Hausdorff measure then. Hausdorff measure is something that you can define in any metric space. And so let me just say for now, in fact, more is true. But so let me just do a quick recall. If you have a metric space MD, and you have a subset K of M, the idea is to cover K with balls. So you define something like mu delta of K. And what you try to do is you have to cover K by balls of radius delta I. With the delta I is less than delta. And then what you try to do is you try to minimize something, and it's something like the sum of the delta I to a power, I'm running out of letters here. Let me do it n. So you try to do that, and maybe you put, there's usually a normalizing constant here, and I don't want to fuss what the CNs are, but they're like the when n is an integer, it'd be something like the volume of the ball of radius 1 in that dimension. And one thing that you see from this definition is that the bigger I make delta, the more ways I have of covering, and so the infimum goes down. And so that tells you that this is monotone in delta, and mu n of K is going to be defined as the limit as delta goes to 0. And you can check that this limiting thing is a measure. Probably even a Borel measure. But of course, it depends on the parameter k, which, by the way, the parameter n, rather. Let me fix this. The limit exists because of the monotonicity of this definition in delta, and the limit depends on n. And to give you a flavor for how this thing works, let me think about a two-dimensional surface sitting in three-dimensional space, say, and so you'd cover it with balls like this. And in this case, we could probably take the balls all to have the same size, so we could take delta I to be equal to delta. And how many balls would you need? Well, the number of balls, of delta balls, would be like 1 over delta squared. And that's reflecting the fact that it's delta squared is reflecting the fact that this is a two-dimensional surface sitting in three-dimensional space. If it was a line or a curve, it would be like 1 over delta. The smaller delta is the more balls you need, but it would only go up like the first power of delta instead of the second power of delta. And so what you would find is that if this n is well adapted to the set you're measuring, then this quantity has a chance to be non-zero and non-infinite. But if the n is too big for the set you're measuring, so if I try to measure like the three-dimensional volume of this two-dimensional surface, so what's the example? The example is mu3 of a surface is going to be 0, and mu1 of a surface is going to be 0, is going to be infinity. And the same thing for, in fact, mu2 plus epsilon and mu2 minus epsilon of a surface is going to be infinity. But mu2 of the surface has a chance to be non-zero, and in fact will coincide with the usual area. For a smooth surface, it will coincide with the usual area. And that's, I have to choose this constant correctly, C2, if I want it to be the usual area. Otherwise, it'll be a multiple of that usual area. And so the general phenomenon is that more generally, for every k in M, there exists n, which doesn't need to be an integer, such that mu of n plus epsilon of k is 0, and mu of n minus epsilon of k is infinity for every epsilon greater than 0. And we call n the Hausdorff dimension of k. And if you're not familiar of the set capital K. And so a very nice example, if you haven't seen it before, is you take the Cantor middle third set in the unit interval, and you can show that the n, this transitional n, where the Hausdorff measure jumps from infinity down to 0, is something like log 2 over log 3. So it's some number, but strictly between 0 and 1. E.g., Cantor middle third set what's it usually called? It's usually called CMT in 0, 1 as Hausdorff dimension log 2 over log 3. And mu n of k, its Hausdorff measure. So that's what Hausdorff measure is. What did I say? I said all this digression was to say that it's a way of assigning dimensions to sets. And what I was saying was that if you have a convex function, then its derivative exists except on a set of lower dimension. And in fact, the dimension is not just, is a whole integer lower than the ambient space. And so so the answer to Joaquin's question is that if you have this additional regularity on B, then then same theorem holds, replacing the hypothesis that this be absolute continuous with mu plus vanishing on all sets of Hausdorff dimension n minus 1. And in fact, you can even do a bit better than that. You don't really need it to vanish on, you don't need mu plus to vanish on all sets of Hausdorff dimension n minus 1. You only need it to vanish on Lipschitz submanifolds of dimension n minus 1. And in fact, Lipschitz submanifolds are almost differentiable submanifolds for C1 submanifolds. In fact, you really only need it to vanish on all C2 submanifolds. I mean, what are called convex concave hypersurfaces. So in fact, it's enough that mu plus vanish on all CC hypersurfaces. And so what does CC mean? It means that, so a hypersurface is something that can be locally written as a graph over a hyperplane. And a CC hypersurface is a surface that can be locally written as a graph, where the graph is given by a difference of convex functions. Differences of convex functions. And this is actually sharp. So as soon as you have a graph of a difference of convex functions such that your measure puts positive charge on it, then you can construct a pair of measures mu plus and mu minus, or you can construct a mu minus for that mu plus, such that the Counterexamples problem does not admit a Monge solution. So that the Counterexamples problem has a solution, but the Monge solution doesn't. And so what's an example? Why is this hypersurface thing relevant? If mu plus, so think about if I'm in the plane, for example, and mu plus is, say, a uniform measure along this segment here, and mu minus is a uniform measure along that segment there. So if mu plus, in other words, if mu plus is Hausdorff one-dimensional measure restricted to the interval -1, 1 cross R, and mu minus is, oh no, I've got the wrong example. Let me change my example. This is an example of something, but not of what I wanted it to be. So let's do mu minus like this. So mu minus is 1/2 of, this should probably have been 1/2, and this should probably be 1/4. Hausdorff measure restricted to, sorry, not cross R, cross 0. And this should be 0, no, it should be, -1, 1 cross the set 1, -1. Okay, great. So what am I going to do in this situation? Well, the optimal thing is that the mass here divides in half, and half of it goes there, and half of it goes there. And the mass here divides in half, and half of it goes there, and half of it goes there. So that's the Counterexamples solution, but it's not a Monge solution because every mine has to split its output between two factories. How do I know this is the Counterexamples solution? Then if I take my convex function u of x1, x2 to be absolute value of x2, then I'm going to get that the subdifferential of u at x1 comma 0, then so the domain of du is going to be the entire plane minus the x-axis. And is that the right convex function? That's not quite the right convex function yet. I think it's close. So maybe I have to add something like 1/2 x1 squared. So that where it's differentiable, when x2 is not 0, the derivative of u at x1, x2 is going to be x1 in the first component and either plus or minus 1 depending on, so it'll be plus or minus sine of x2. The subdifferential at 0 is always a convex, at this point here rather, is always a convex set, and it's going to be exactly the convex set interpolating between the plus and minus 1 here. So it's going to be the set x1 cross the interval minus 1, 1. And so that tells me that the output of this point here has to go somewhere in this interval that stretches from minus 1 to plus 1, but the only demand is at the endpoints plus and minus 1. And the only way to satisfy that demand is to send half each way. So my claim is you can check that taking gamma to be, I don't know if I can write it down as drawn. Of course, the support of gamma is something in 4 dimensions, which is a bit awkward to draw, but I hope it's clear what it's supposed to be. Questions? So this was an example where the mass concentrated on something that was an integer, a lower dimension, 1 dimension down, a hypersurface, and we didn't have a Monge solution. And so since the theorem is about existence of Monge solutions, you need some hypothesis to rule this kind of example out. And the hypothesis is that mu plus had better not put positive mass on codimension 1 objects, or objects smaller than codimension 1. Okay,
thank you.
Yep. I wanted to talk a bit more about Brenier's theorem. So Brenier actually, his motivation was something a little bit different. His motivation was something like, if you have a measure on Rn, and I think that he actually had in mind that mu plus was like the restriction of Lebesgue measure to some set, omega plus compact. Divided by its total mass to make it a probability measure. And a mapping, whatever measurable, and he actually had some assumption like the integral of s squared, the integral of the magnitude of s squared against mu plus should be finite, but it's not too important. But such that f push forward mu plus is also absolutely continuous with respect to Lebesgue, or at least doesn't concentrate on subsets of codimension 1. then his conclusion was, then there exists U convex and a mapping S from Rn to itself, such that two things happen, such that F can be written as gradient U composed with S and almost everywhere. And S pushes forward mu plus to itself. So this was what he called his polar factorization of maps. Actually, he called it, and this caused a lot of confusion for about 10 years. He called it a polar factorization of vector fields, but it's actually a polar factorization of maps. And when you have an object taking Rn to Rn, it's easy to get confused as to whether it's a vector field or a map. But okay. And so basically, how does this work? Well, and he made several observations. So in fact, maybe I want to, let me set this theorem aside for a moment. And are we doing on time? Let me do an example first in this context. So, so if I take M plus and minus to be Rn and B to be the inner product, and I take, this is sort of, this example is a statistician's dream. So let me have, suppose I have matrices, n by n matrices, sigma plus and minus, which are symmetric and positive definite. And then you set, and you consider Gaussians. So in other words, measures whose density with respect to Lebesgue is like e to the minus 1/2 x sigma plus minus x dxn. So i.e. mu plus is Gaussian, mean zero, and covariance, I think sigma plus inverse. Right, so in other words, if sigma's large, the Gaussian is going to be very concentrated and its covariance is going to be small. And if sigma plus is small, the Gaussian is going to be very spread out and its covariance is going to be large. Right, the covariance is basically it's the matrix whose entries are integral over Rn of xi xj d mu plus x. And then you can ask, what does the optimal map G look like between these two things? Does anyone know what the answer is? How do you think you get from one Gaussian to another? How about in one dimension? What would the answer be in one dimension? So for example, you have a sharply peaked Gaussian, you want to stretch it out and make it a flat Gaussian. What map do you think is going to do that? So it's maybe not so obvious, right? So this is one of the few cases where you can find the convex function explicitly, and that's because the convex function has a very simple form. And so the claim is that the map is always linear. where u of x is 1/2 xqx. And so to be convex, since this expression is symmetric in X, it doesn't cost any generality to take the matrix Q to be symmetric and its indices. And since U is supposed to be a convex function, Q would be positive definite, non-negative definite. And so what does that mean for G? It means G is QX. For a suitably chosen Q. And how do I verify this claim? Well, so what's the effect of the image of Q push forward mu plus? You know, the effect of that is going to be, is going to have density something like e to the minus 1/2 x, and then I can't remember if it's a q or a q inverse here. So let me put q plus or minus 1, sigma plus rather, q to the same plus or minus 1. Sorry, and of course there's a normalization constant so that it integrates to 1. And the constant, of course, depends on sigma. It probably depends on, it's probably like the n/2th root of the determinant of sigma or something like that. Hence covariance. What's the new covariance is going to be something like sigma plus inverse q minus plus 1, q minus plus 1. And so basically what this, so what I say is true if we can find a q such that this covariance matrix agrees with sigma minus inverse, then I'll be, and if, as long as q is non-negative definite and symmetric, I'll be done because I'll have exhibited a convex function whose gradient pushes forward mu plus to mu minus. And so the whole question boils down to, does there exist a q? I think it's probably the minus sign is correct. So it becomes plus in this context. So the whole question boils down to, does there exist a positive definite q that satisfies this equation here? And I guess probably I want the covariances to be strictly positive definite here so that I could invert these matrices. And does everyone, how many people know what a matrix square root is? Does someone want to remind the class what a matrix square root is? Did anyone put their electronic hand up? Well, okay. A matrix, oh yes, it's in the chat now. Right, so the matrix square root of B is a positive. So first of all, B had better be a positive or a non-negative definite matrix. And if B is a non-negative matrix, its square root is another non-negative definite matrix A, such that symmetric, so the transpose is kind of irrelevant here, such that A squared equals B. But so since these sigmas are positive definite, they, in some basis, their eigenvalues are all real and positive. And so in that basis, you take the square root of the eigenvalues. And that's how you get the A from the B. And so what do I claim Q is? I claim Q is given by some pretty hideous formula, but it looks the following way. It has, I think it has sigma plus to a power, and then sigma plus to a power, and then in the middle it probably has sigma minus to a power with sigma plus on either side. And there's a matrix square root here. And I think this power is probably -1. And so these powers are probably +1/2. And this is probably +1/2. So I claim if you plug that Q into this formula, miraculously it works. And let's see the magic. So sigma plus to the 1/2, sigma plus to the 1/2, sigma minus inverse, sigma plus to the 1/2, matrix square root, sigma plus to the 1/2, and then there's sigma plus to the -1, and then there's another sigma plus to the 1/2, and then there's this bracket again, and then there's this sigma plus to the 1/2 out here, and inside the bracket is sigma plus to the 1/2, sigma minus inverse, sigma plus to the 1/2, and then this matrix square root. So these guys cancel with this guy. These two brackets have the same thing together, so they multiply to give that to power 1. And that to power 1 is sigma plus to the 1/2, sigma minus inverse, sigma plus to the 1/2. And then I have a sigma plus to the 1/2 and sigma plus to the 1/2 on the outside. And so maybe this should have been minus here. And then these guys would be minus, and then these guys would cancel out. And then that would go that. So I guess maybe it's this. Anyhow, so there's some formula. And okay, so you take a positive definite matrix, you conjugate it by positive definite matrices, namely these negative square roots. And you get another positive definite matrix, so you can take a square root again. And you conjugate that by positive definite matrices. This formula miraculously works. And so now since I've shown that this formula works, I've exhibited a convex function whose gradient pushes forward the first Gaussian to the second Gaussian. By the uniqueness of our previous theorem, it's the unique solution. And there's this formula has kind of an interesting history. So this formula was found by 4 different groups of statisticians something like this formula was found by 4 different groups of statisticians between the years 1980 and 1984. So before the work of Brenier. And so 2 of the groups of statisticians forgot that matrices don't always commute with each other. And so they wrote down a formula that is not correct, but only works when sigma 1, sigma plus, and sigma minus happen to commute. So that the same basis does all the diagonalizations for you. And the other 2 groups of statisticians got it right. Okay, so that's a nice example.
So Robert, what problem were they looking at? Were they like doing optimal transport between these 2 Gaussian measures, or was it something different?
Yeah, I mean, they would not have used the terms optimal transport, but they would have said, I have 2 random vectors, and I want to know how well or how badly can they be correlated. What's the maximum and the minimum of the correlation? So that's an equivalent question. 2 Gaussian random vectors with given covariance matrices, what's the maximum, what's the maximum positive and negative correlation they can have? I think, let's see, let me see. One of the groups is Dowson and Landau, one of the groups is Olkin and Pukelsheim, maybe Rachev and Ruschendorf were one of the groups, I don't remember, and I don't remember who the 4th group was. Short, Givens and Short. And I guess they were all statisticians. I guess they were all motivated by kind of similar considerations. Okay, so now let's come back to Brenier's theorem, which was about this polar factorization of maps. And so let me try to sketch a proof of Brenier's theorem. And here the hypothesis is that I guess I want both the measures to be absolutely continuous with respect to the leg. So both mu plus and its image under F to be absolutely continuous with respect to the leg. And so the idea is that when in our theorem, we just needed one of the 2 measures to be absolutely continuous with respect to Lebesgue. If both m plus and m minus are n-dimensional manifolds, and both are absolutely continuous in coordinates, then also there is a map H, let's say, from M plus to M minus, mu minus, such that H pushes forward mu minus to mu plus, and H is sort of the B tilde exponential of the conjugate of U gradient, and G composed with H is the identity, mu plus almost everywhere, and H composed with G is the identity, mu plus, mu minus almost everywhere. So in other words, when both of these mappings, both of these measures rather, are not concentrating on lower dimensional sets, then the mapping is invertible in an almost everywhere sense. And this is not too hard to prove. So this is basically about invertibility. But probably that's the proof is all I'll have time to do, and then I'll have to talk about Brenier's polar factorization theorem next class, I imagine. So the proof is that, let's think about our previous proof. Let gamma be optimal again. Oh yes, I should have said, and B tilde yx equals bxy satisfies the same hypotheses. So in other words, I need the twist condition with the role of y and x interchanged, and the Lipschitz differentiability. So let gamma be optimal again, of course, and let gamma tilde be kind of the reflection of gamma under the interchange of x and y. So of course we had support gamma is contained in the graph of the subdifferential of mapping B, but we'll also have support of gamma tilde contained in the B tilde subdifferential of U conjugate. Right, this is a subset of M plus cross M minus, and this is a subset of M minus cross M plus. And we'll have, by the same proof, we'll have gamma tilde will be identity cross H, push forward mu minus, where H is as above. And so, but so what the basic idea is that the difference, so if I looked at this thing, and if I intersect it with the domain of du I cross M minus, I have a set of full measure. This is a set of full measure for gamma. So that's basically gamma almost everything. And I could also intersect it with M plus cross the domain of the gradient of U conjugate. And that would be full gamma measure because I've imposed symmetrical hypotheses on the plus and minus side. And this is basically, this intersection is basically a part, is something like graph of G intersected with this. And the other intersection, so this is contained in the graph of G, but it's also contained in the reflection of the graph of H. So let's call it the anti-graph of H. And so a point, in other words, a point in here is in here if and only if y equals g of x, and also if and only if x equals h of y. And so that somehow shows that on this set of full measure gamma, h is acting as an inverse map for g. So I get these two conditions that I had asked for. Are there any questions about that? And so this invertibility, when I have symmetrical hypotheses, is what will allow us to prove this polar factorization of Brenier's theorem at the beginning of next lecture. And then also next lecture, I promised. So Hernyi Chen last class in office hours had, is there some way to understand that the support of the optimizer is going to sit on this graph or this n-dimensional subset of this 2 n-dimensional space? And I said, yes, and I will show it next class, but I obviously didn't show it today, so I'm going to show it on Thursday. Any questions before I pause the recording? If not, we'll pause the recording and transition to office hours.